Good afternoon, 216. This is CJ. Today is Monday, November 4th, week 11. Today we're going to be going over part 1 of Lab 9. So go ahead and download yourselves the code distribution and let's get right into it. All right, so today we're going to be talking about this forkme.c file, and we'll be answering the questions.txt. So we have just finished up assembly, and now we are moving into system calls. The system call we're focusing on this week is mainly the fork system call, as well as a few others like get PID, get PPID, fflush, and looks like that's just about it. And wait, but that will be on Wednesday that we'll talk about that. All right, so to understand what system or what the fork system call is, we'll have to first talk about processes. So what is a process? Well, it is simply defined as an instance of a program run by at least one thread. And a thread, threads we will talk about in future labs, so we won't worry about those for now, but just know that they exist. And yeah, okay, so that's the simple definition of a process. It has its own address space where the 4 logical regions of memory live. These are the code segment, the data segment, the stack, and the heap. We've learned about those plenty. And one thing to know about processes is that since each process has its own address space, they cannot access other processes' address spaces. That is, unless these processes are communicating through inter-process communication, whether that be message passing or shared memory where they can access one another's address spaces, at least a small portion of them, or pipes or other inter-process communication. All right, so the reason why we're talking about processes is because fork specifically deals with spawning new processes. So our main program, when we compile and then run it in a terminal, the shell that we're using is going to use some kind of fork, or I guess exec system call, and is going to create a new process to run our program. And the entry point in C is the main function. So we have this new process running, and I mean, just as normal code runs, it's going to run top to bottom. And once we get to a fork, we can then split, well, not exactly split, but create a new process to run this program. Okay, I'm jumping a little bit ahead of myself. So first, let's just look at what's going on here. We have a printf that says start, and it prints out the PID, the process identifier, and the parent PID, the parent process identifier. So each process, let me open up my terminal, each process has its own PID, and that is unique to the process. If I type PS, the PS command, we can see I have a few processes running right now under my user, I guess, related to this shell, and that is TCSH with the PID of 17726, ZSH, which is my shell, 17789, and the process 23414, which is the PS command that I was running at the time. So we can identify processes by their PID. We don't really care about the command right now because multiple processes can be running the same command. Let's say I opened Vim, and then I suspend Vim but don't quit, and then open Vim again, a new Vim, and suspend that one, and type PS. well, we see I have two VIMs running. One of them is going to be running on 23562, and the other is 23568. All right, so we call processes by their PID. And so this program, what it's doing is it's saying start, and it's printing out the current PID and the PID of the parent. A process's parent is the process that called the current process. And then we make this flush system call, which is targeted at std out, standard output. And this is to, well, as the comment says, to prevent I/O duplication. So what this does is output streams like std out have, or will often have a buffer that has everything that is going to be printed, and sometimes it just doesn't print everything, whether because usually it only prints when it reaches the end of the buffer or when there is a new line. And so what flush does is it just makes sure that it clears out that buffer, and so it prints everything in standard out to the screen when you call flush. So in this case, we're going to make this printf, then ensure that that's printed out, because otherwise we could have run into problems later down the line when these forks are being called. For instance, if we call a fork, spawn a new process, now we could have two processes with this start in the buffer, and well, then this start message would get printed twice. All right, so that's what this flush system call does. And then we start this for loop that we're going to be looking at. And we notice that we run through this for loop 4 times, and we increment this global total integer. And then we're going to call fork. Okay, so what is fork? It spawns a new process running this exact same program at this exact line of code. So we start with one process, and then once it gets to a fork system call, it creates another process, and now we have two processes, again, separate from each other, running the same program from this line of code onwards. So the child process, which a child process is the process being spawned from this fork, the child process will not run this code up until now. It will run everything continuing on from there. Now you may ask, CJ, what about all of these depth and global total variables? What happens with the child process? Well, the answer to that is everything in memory from the parent process is copied over to this new child process's address space at the time of the fork system call. And so the new child process will have not a reference, but a copy to this global total variable. So notice how we incremented it. It goes from 0 to 1 in the parent process. Then we call fork, and the global total for both processes will be equal to 1. Okay. And then the last thing that fork does when it returns is for the parent process, it will return a PID t, which is basically just an integer saying the PID of the process that it just created, so the process identifier. And for the child, it will return the number 0. And so this next line is checking, is this current process the child process? Because if it is the child process, then this child variable will be this child PIDT will be set to 0. So we can check that here and then go into specifically or a child-specific region of code. Now we see a little comment that says to do insert code that makes the parent do some stuff. We will talk about that on Wednesday. Okay, so that's the end of this for loop. We run through this for loop 4 times. And then after that, we do a little for loop for the depth. This depth has been incrementing every time we get a new child, only for the child, not for the parent. So further down children will be at new depths. And then we print, very similar to this start message up here, we will print a finish message with our PID and the parent PID. And then finally we will return the global total. Okay, so what do we expect to see in the output when we run this? I'm going to make, and someone shout at your screen what you expect to see. How many print statements, apart from this first start, how many finish print statements do we expect to see here? 4, 5, 112? Let's see. Oop. Let's just fork me. Okay. So if we count through all of this, we see we have 15, not 15, apologies. We have 16 finish statements, as well as this one start. And let's look. We started with our parent PID. Well, the parent that we start with has a PID of 28100, and its parent, which is our shell, so ZSH is going to be 17789, and we see that up here. So the shell called our fork me program, and so therefore it is the parent of the program. And then let's see, it was the first to finish, and it printed that this is its PID, this is its parent PID. Then we start seeing the children printing. So we have PID 28102, and its parent is, well, that's the original parent here. And on and on. Okay, so why did we see 16 prints and not something like 4 or 5? Well, if we drew this out, I don't have anything to draw on right now, but if we drew this out, at each iteration, we make a fork call. So the first iteration, there is just the parent, and it calls fork, and it makes a child. Now, we continue running both iterations from this point on. So I gets incremented to 1 for both of them, and they each make a fork call. Okay, so now we have 4 processes. I is 1. It then increments to 2, and then we do another fork call. So we go from 4 to now 8 processes. I increments to 3. We do one more fork call, and then we get 16 processes, and then I increments to 4, and is 4 less than 4? No, it's not. So we break out of this for loop, and we go and we, each process does its own print. Okay, so that is why we see 16 finish statements. What other things do we see here? Well, one, we see this global total variable is 4 for every single one of these. Again, that's because memory gets copied over to the new address space when a fork call is made. And so in this for loop, we increment global total. It starts at 0, but then we increment it, and the parent's copy of global total gets copied over to, or the parent's version of global total gets copied over to the child, and it can pick up at 1. And so we end up seeing the same for all of the processes. Okay, and well, let's see. We have a few things to talk about. One, we see that some of these parent IDs are 1 rather than one of these other processes. So why is that? Well, the original parent here, 28100, it makes these fork calls, but then it's a pretty short function, a pretty short program after that. So it's going to print its finish call, or its finish statement, and then it's going to return. And when a process returns from this main function, it's just going to exit and disappear from existence. So in this case, we see that some of these finish prints get printed just fine. So their parent is still running, but some of them, it looks like the parent has disappeared. And all processes have to have a parent process. And so these orphan processes where the parent has exited, they get adopted by the process number 1. Always. Every time they get adopted by the process number 1 if the parent has disappeared. Okay. And here's the other thing, is what is going on here? Because let me clear and run again. We have our first prompt where I typed fork me, and then we start printing, and then we have a prompt, and then we keep printing, and now we're done, but we don't have a prompt. I could type something like ls, and it is actually running the command ls, but for some reason, we have clobbered our prompt. So why is that? Well, remember that the shell here is just a program that runs another program. And once it's done running that program, it's going to print a prompt, assuming that we are ready to type another command. And so here, the parent process, the first program that started running, it has exited at some point. We see all these 1s. It has exited, and then, well, the shell was just waiting for it to exit before it could print its own thing, its own prompt. And so even though other processes are running and trying to print to standard out, because the standard out here is going to be this terminal window, even though these are running, the shell doesn't really care about that. The shell just cares about its one child, which was the original process. And so it prints, and then in this case, it was just 2 other processes print, and now it's just waiting for our input. If I press return or something like that, well, now we see our prompt as normal. Okay. What else do we have to talk about? Okay, finally, let's talk about the ordering. Do we see any pattern in the ordering? Okay, well, we can easily see from our depth that the parent, the original parent, finished first. Then we get a child of the parent, a child of the parent, a child of the parent, then a grandchild of the parent, grandchild, now another child, then a grandchild, and then a great-grandchild. And after another great-grandchild, we go back to a grandchild. And way down here, we have a great-great-grandchild. Okay? So let's see. Parent, 3 children, 2 grandchildren. Let's just stick with that for now. And we'll run again. Okay, now we see a parent, 3 children, and 3 grandchildren. And let's try again. Now we see parent, 3 children, 1, 2, 3 grandchildren. Trying to get a more interesting. Okay, here we see a parent, 1 child, 1 grandchild, and then 2 children. So we see that there is no particular order that these finish. And that's because these processes have nothing to do with each other. Yes, they may share a standard out that they're printing to, and yes, they may have come from some parent, but they don't, once they're off in the real world, they don't really care about each other unless we tell them to, and we'll talk about this more on Wednesday. But they're just going to race to finish as soon as possible because that's the goal of a program, is to not be programming anymore, I guess. They're sick of their job. They just want to get out of there. So whoever gets to this print statement first will print. And then they can be done. And the other ones who are lagging behind, well, you snooze, you lose. Okay, cool. So is there anything else to talk about today? I don't think so. Okay, let's look at our questions.txt. So, blah, blah, blah. We've done this running and compiling and running. Okay, here's the question. How many total processes are created by running this program? Well, we could... there was one more thing I was going to talk about. Okay, well, we could go and count it out like this. We could go 1, 2, 3, count down to 16. You're just going to have to trust me or count for yourself that it is 16. Or we can actually calculate this. So looking in here in this for loop, we see that we run through this for loop 4 times. Now that number is significant because we do a fork on every single run of this for loop. There are no special breaks or if statements that make it so that we sometimes run through this for loop. We do for 4 loops for the parent process, and every single one of those we do a fork. Okay, we can calculate that through the use of 2 to the power of the number of times we call fork for the parent. Now, this doesn't always work. Sometimes you may be tricked. Let's say we have like if I mod 2 equals 0 or something like that, and it's mad at me. Oh, because... yeah, whatever. Something like this. Or we had, I don't know, what else could we have? Something like this and then a break immediately. We would only do fork once. That number is going to be different. But in this case, where we run through this for loop every single time, and every process that goes through this for loop makes a fork, we get 2 to the power of I here. 2 to the power of I processes are the result. Okay, so what is 2 to the power of 4? Pull out your calculator, do it in your head. It's 16. Okay. Next question. Which of the following best describes the relationship between the processes created by running this program? Is there a chain of processes with a single parent, a single child, a single grandchild, etc.? So this would be like parent, child, 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 on and on, where this parent is the parent of this, it's the grandparent of this, and the parent is the great-grandparent of this. So is it that? There's a fan of processes with a single parent. So the one parent is a parent of every other process. There's a lopsided tree of processes with a single parent, several children. Some of those children have have their own children, which are grandchildren of the parent. Some of those grandchildren have their own children, which are great-grandchildren of the original parent. Or are there 7 individual parents, each of which has a single child? So I don't even know how to draw this out. Well, if we were in person, I'd draw this out on the whiteboard, all of the fork calls, but you can do it for yourself. Just draw a single circle, and when there's a fork, draw an arrow from that circle and make a new circle. Okay, that is the new child. Now the next fork, each of those draws their own arrow and their own new child. Hello, this is late night post-processing CJ. I just wanted to draw out what I was trying to explain in the lab video for you all. So basically, let's say we start with our parent. Okay, our parent has a variable I that starts out as 0. Then we do a fork. Let's make this red. This is our first fork, and this is going to result in child 1. Now, for both of these, remember, child 1 gets a copy of every variable from the parent. So I starts out as 0 for both of these. And then we pick up execution right after the fork call. And so I increments to 1 for both processes. Okay, so now we move on through the rest of the for loop. We come back around to the beginning and we get to the next fork call. Okay, new color. Parent creates a child 2, and child 1 creates, well, let's call this grandchild 1. Okay, now again, for all of these, I is set to 1. We now increment I to 2. And we go back around with a new color. So we get child 3 for the parent. Then child 1 needs a child. So this is grandchild 2. Yep. Child 2 gets its own child. Grandchild 3. And then grandchild 1 also gets a child. Yes, we are still in green. Great grandchild 1. Okay, now for all of these, I is 2. It then increments to 3. And we move on to orange. And we go again. Parent gets its final child 3. Child 1 gets another child. Great, nope. Great grandchild. What are we on for grandchildren? 4. That's in the wrong place. Well, all of these need children. It doesn't really matter what direction we go. So let's call this grandchild 5. This is grandchild 6. My handwriting's horrible today. This gets a great grandchild. What is that? 2. Everything that isn't orange gets a child. So this gets a great grandchild 3. Running out of room. This gets a great grandchild 4. And then this gets a great grandchild 1. Okay, every single process has a orange child now. Okay, and then for all of these, I was 3. It increments to 4, and remember that our for loop was I is less than 4, so it breaks out of this for loop now. And if we count these all up, we have, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 processes. So that's how we create all 16 processes if we were to draw it out. And you can see here that, yeah, it's like a lopsided tree. We don't have the parent having all children. It only ends up having, these 4 children. We also don't have a line, and we don't have whatever the other thing was, which was like something like that. I don't even know. Okay, back to me from before. And once you've drawn out this whole tree, it ends up being this lopsided tree. Any questions so far? No, you all are being quiet today. That was dumb. Concerning when the processes complete and produce their finished output, is the order that the processes complete always the same? Well, we talked about this. No, it is not. Is the entire output order varies and cannot be predicted? Sure, sounds good. Portions of the output appear predictably, but other portions vary. Maybe, I don't know. Only the process IDs vary, but the printing order does not change. We didn't observe that, so I'm going to say it's this for now, and we'll see if I'm right. Okay. Last question. Check all that are true about the initial version of ForkMe program. Sometimes when running the program, a process will report its parent ID, its parent PID as 1. Yeah, we saw that. All processes report a global total of 4. Yep, we saw that too. Sometimes the start message will appear after some finish messages. Well, we talked about the F-flush, and we know that it's not true. And finally, the intended output of child and grandchild processes print more minus symbols does not work. And all processes appear at the same level. No, we saw minus symbols, so I think we're good. And that's the last question. So now we can just do make test code to verify. I think I messed up. Okay. Give me a minute. All right, apologies. There was a bug in the testy script that we talk about here. We also made a Piazza post about it. This is how you fix it. That's how I fixed it. Just remove testy and then get yourself a new one. Although I was also, that's my homework. Although I was also doing make test code, which is not what I was trying to do. We should be doing make test quiz. And there we go. Those answers are okay. All right. That's everything I have for you for today. Thanks for watching. Like and subscribe. I'll see you all next time.